All right, well, I guess we're going to talk about the other FP today. As a former numericist, I always get confused when I talk to functional programming people and they start talking about FP, and I'm on a different wavelength the entire time. So I first started doing serious computation using floating point numbers. I was writing a code to model the corrosion of surfaces. And it turned out, as I put this code together, I had three different problems. The initial challenge was that this is the first time I had written code on a cluster. This was probably around 2009 or so that I started this project. And so I had to get used to the MPI system, which is the message passing interface, which is just, the distributed systems. Typically you just chop up your domain in rectangles and you partition it out among everything. And it's a really straightforward late 80s, mid 90s view of what concurrent computing could look like. And as I developed this code, I ran into three different categories of problems with it. The first category of problem was that the equations I was solving were what are known as very stiff equations, which means that different parts of the numerical system that you're solving are affected by different time scales in the differential equations that you're trying to solve, which means that certain techniques may work better or worse, and you have to start worrying about matrix conditioning and other aspects of this. And it gets really messy, and it's a very mathematical kind of fix. The second I ran into was getting different kinds of deterministic errors that I could trace down. Typically, not always, but typically these were related to bugs in the system and sometimes to just having to refactor algorithms and figure out what was going on with that. And the nice thing about deterministic algorithms is once you understand where they're coming from, it's moderately straightforward to either sidestep them or work around them, or at least compensate for them because you understand where they're coming from in the system. And then the third condition, the third kind of error that I ran into when I started doing this were non-deterministic errors. And of course, I didn't call them this at the time. I had a much ruder term for them. But what I was seeing in particular was that even when I would give my algorithm the same random seed, for instance, I would get different results. And what's worse is that the results seemed to be actually bound to the topography of the processors that I was using in the communication. And this is really bad when you're trying to simulate something like, why is this happening? And as it turned out, in that case, that was the first time I ran into the non-deterministic error of race conditions. Now, with the floating point errors that I'm going to talk about here, I'm not talking about race conditions, but it's the same sorts of patterns where things are going wrong in a way that's not always straightforward for you to predict numerically what's happening or why it's happening. And to start us off here, see if that'll load. Okay. So, for whom does this make sense? Okay, about half the room. We're doing pretty good there. So, the joke here is, okay, so if you've worked with floating point numbers before, you may have run into cases where you've done something like overflown to an infinite value, or you've been working with some very small value close to zero. You underflow it to zero, and then you do a division by that value. You get a division by zero, and your result is not a number because 0 divided by 0 is not defined. NaN has some interesting properties. For instance, that one NaN never compares equal to another NaN. The point of NaN is that it blows up everything that it touches. Now, the nice thing about NaN, so there are some bad things about NaNs when they infect your calculations, but the nice things about NaNs is that it's an extremely good signal. Something has gone wrong. You've done some bad math, and you can trace this down, and you can do it. Now, since knowledge about floating point mathematics and their quirks is unevenly distributed, unless you've done the kinds of numerical analysis that require you to do this work, I'm going to do a quick refresher on the structure of IEEE 754 floating point, which is the common kind of floating point that you run into on systems today. There are some others like bfloat that are implemented on GPUs and for some LLM systems today. So there's starting to be some new things for the first time seriously in 20 or 30 years. But for a long time, 754 was the only standard we had. And the crazy thing about floating point mathematics is that apart from a general exhortation to be careful and know what you're doing, there's little of practical use that can be recommended to get these things right sometimes. It's actually kind of funny that we've been doing mathematics on a computer for so long, and yet we still have some interesting problems with it. So fundamentally, the problem that you have to solve is when you are writing down a number that has a fractional part, a part that is not a whole number, how do you represent that? And anciently, people experimented with different systems. Improper fractions were often settled upon. Decimals were invented in the medieval Arabic mathematical world. But for instance, if you go look at Napier's invention of logarithms, most of the time he's actually using very large numbers, numbers on the order of 100,000 or so, rather than explicitly using decimals, because no one's really quite comfortable with decimals yet. But it turns out that if you want to capture the idea of a number with a fractional part in a base 10 system, or really in any system, because you can alter these quantities, you have to specify three things. You have to have a sign bit, a sign quantity, some way of indicating positive or negative. You have to have a mantissa, which basically means or sometimes it's called a significand, but it's basically the magnitude of the number. And then you have an exponent, which is basically it's a sliding scale. It's to tell you how far to the left or the right. Now, you run into these all the time. Sometime in high school, you start to do, you run into engineering notation on your TI-84 or whatever you're working with. And you get used to this kind of idea that sometimes you write like an E3 or E-3 after your number to get that right. Now, what we're going to do with the computer is we're going to speak binary, which means that we have to have some sort of system of fractional expression that we can use in practice. And so what we're going to do, go ahead and drop all these in. Okay, so we are going to, this is a 32-bit single precision C float. And what it does is it defines certain bit windows to characterize exactly what's going on with this number. The nice thing about this IEEE 754 approach is that certain things are baked into this protocol so that you know that they're there. For instance, whether your sign is 0 or 1, fine, you just pick one. The exponent is with a bias, which is an interesting solution because you have this problem where you have 8 bits to indicate a numerical sign, right? A numerical exponent in binary. The bias is there, which means you subtract 127 from it by default so that you can indicate exponents that are smaller than 0. So you can scale it down. But that's baked in. You know that's there, so you don't have to specify. You don't have to worry about if you're specifying a negative number or if you're doing like a 2's complement or a zigzag or anything else like that. It's just you know that you're subtracting 127 from it. And then you have the mantissa or the significand at the end, which has an implied leading 1. So you get the 1 for free. So you sort of get an extra bit in your value there. And you get to put these together and do mathematics with these. Now, there are some quirks. There are certain bands of the exponent that if certain fields in the exponent are filled, it means you either have a nan, you have one of those not a numbers, or it means you have a positive or a negative infinity. So that's indicated here in the exponent, which means if you hit one of those, you're actually missing a whole swath of numbers in the mantissa that are kind of wasted space in a way. And there's some interesting tricks that people do with what's called nan packing, where you can generate an invalid number and then you can pack data in the mantissa to carry information about what's going on. But in general, this has been a good enough solution for most of the things that have gone on with us. And so if we're going to calculate a value using that, we can, there we go. That's one. Okay. So, you'd walk through, you'd subtract your bias out, you'd calculate your values together in binary, right? That's a binary point, not a decimal point. So we have to do that conversion into decimal. And then we arrive at something that in decimal, we would write this way. That's the equivalent to that value. So we can carry this around. We can do interesting things with it. Now, there are some very interesting ramifications of the kinds of things that happen from things like the exponent. So it turns out that your exponent is granular. What this means is that if your exponent is is at a fixed value, and you have a significand of a certain size. You have I'm calling it a mantissa here. I'll try to stick to that notation. If you have a mantissa of a certain length and you change the exponent by 1, now you're multiplying it by a different exponent as a power of 2, and things get slid around. The granularity, the resolution of the number changes. And so different parts of a floating point calculation can have different, basically numerical horizons of the kinds of information they're seeing and are interacting with. Another one of the ramifications of this is that when you run into a number that is, so in decimal, if you do the number 1/3, what happens when you try to write that down in decimal? Right, like it repeats, right? It's 0.33333. And the reason for that is that 3 is not a factor of 10, and so there's no terminating way to write that without repetition. And 1 divided by 7 does the same thing. And people who like to get into weird number systems are always like, well, this is why you want to use power of 12. But the problem is that the same thing happens in floating point, but it happens with respect to powers of 2 instead. So, back when I used to teach Intro CS, this is one that I used to love to blow my students' minds. So in floating point, this is an example in Python. I can do 1.1 minus 0.3 minus 0.8. I get the binary representation of it. This comes to exactly 0. If I do the same calculation in a different order, 1.1 minus 0.8 minus 0.3, I get a different answer. Do you have a comment, or are you just? Yes. Because the exponent is 2 to the 0 powers here, and then you subtract the bias off. So you subtract the bias off, and then 0 is actually a weirdly special case too, in that you can have signed 0. So you can put a sign in front of the 1, 0, 0, 0, like the other 31 bits are also 0, and that picks up as a negative 0, a signed 0. So you could think of, because you're right, there is an implied 1. So there's kind of a case in which 0 is special cased in the same way that infinity is special cased and nands are special cased. But the treatment is correct by the machine when it runs into it, even though it's a little bit special in that way. Yes. It's hard, like it's part of the protocol that there is a bias of a certain value. So if you were doing 64-bit, if you were doing C doubles, it would be a different bias. You'd arrive, you'd have a different bit width. I think maybe it's 12. I don't think it's 16. Anyway, you get a different bit width than 60. This is actually a place where you mentioned that implied 1. The implied 1 shows up in this calculation because that 1 is still implied there. So when you do this bias on the exponent here, you end up with 5.5 whatever times 10 to the negative 17. It's really tiny value, fantastically tiny value. And this is why you always tell people, right, like you ignore absurdly small numbers. Now, that's a problem, isn't it? That we do the same math, but we've lost associativity and we've lost commutativity. Both those properties are gone here, right? And it makes it actually really hard to reason about what precisely should be the result when you do any calculation in floating points. Now, most of the time, we don't care, right? Like in the sense that, if I'm calculating like 3D graphics on a screen, I can't see this value. If I'm calculating physical forces, like in an atom, for instance, maybe a number like this would matter, except that if you're really doing that kind of thing, you need to scale factor everything so that you're within 3 degrees of magnitude of 10 to the 0. So there's a sense in which for a lot of the problems that are out there, this doesn't matter. And it's one of the reasons it hasn't really been a concern to fix this, try and make this problem deterministic in the same way. Now, this is one kind of error with floating point. This is a deterministic error because it's repeatable. You do this on any system, assuming you have the same rounding mode, et cetera, you're going to get the same answer on any system. So you can build around it. It's a little bit hard for some reasons we'll get to later on, but you can do it. All right, let's see. All right, and then every now and then you get a world where these things become macroscopic. And so here we have an example of, this was a computer system that was representing its clock value in tenths of a second. This was a late 1980s computer system, which means that the machine truncation for 0.1 was actually 0.999999905, which means we can calculate what the error term was. It's everything that didn't fit in the bit representation that it had there. And in practice, what this meant is that if you left the system running for 100 hours, you had an error of 1/3 of a second on the system. This system in particular that I'm talking about here was a missile interceptor system in the Gulf War in 1991. And it missed a missile, which hit a US barracks. And they actually knew, and it was in the protocol, you're supposed to reset this machine every 2 days. They were trying to avoid this exact situation, and it didn't happen, and they got outside of margin there. So, occasionally these things do get macroscopic. All right, let's see. I talked about the sliding exponent window there and what goes on with that. Now, okay, so before we talk a little bit more about floating point, I want to talk about deterministic computation. And so I work for Urbit Foundation. There's been a couple of Urbit talks today. And one of the things that Urbit as an OS is trying to do, one of the properties it wants to have as a functional operating system, is it wants to have referential transparency. Excuse me. It's been a while since I've talked this long. The system wants to have referential transparency. One of the characteristics of that is that you can replace any function and its inputs with what the output of that would be, and that you can do it completely deterministically. Now, you might say, okay, for Urbit, maybe this is a bit of a conceit. It's a thing we're trying to do, right? But there are other systems where you actually want this exact determinism. So if you're running something on a blockchain, let's say you're doing a calculation on a zero-knowledge proof blockchain or even on EVM, and you want to post information about this, two people running that same computation on different systems at different times with the same inputs should not get different answers, even in the tiny bits of what they're trying to calculate. Another place that really cares about determinism, it turns out, this one kind of surprised me because I hadn't thought about it, is forensic accounting. That you want to be able to show legally that a system is exactly adhering to a certain standard's behavior and specification here. And let's see, code correctness analysis relies on this. Verification and validation. And a lot of the programs that are out there in like National Lab System rely on this. Like you actually want to have complete predictability about every piece of the system, even if it's buried in the very small bits about what's going on. Now, what this means is that we want reproducible determinism across platforms, even if we're so unfortunate as to have to work in floating point instead of in pure integer mathematics. Now, Urbit holds a few principles to be true. And the objective of these is that we're trying to avoid what we call the ball of mud anti-pattern in software design. Is that we want the system to be deterministic and reproducible because we want it to be amenable to reasoning about. We want to make it so that when you reason about the system, you can predict what happens in every part of the system. Now, there are parts of the system, like networking and so forth, where this is a lot more salient than floating point, and I'm down in the weeds. But I enjoy that part of the world, so I'm going to keep running with it. To a large extent, I believe the current generation of computer programmers have never lived in a world where determinism of this kind has been possible. IEEE 754, which is the current standard, was first standardized in 1985. It represented a compromise across many hardware vendors, software vendors, operating system manufacturers, And it was a way of trying to address a lot of long-standing issues. People had rolled their own versions of this, for instance, in the past. Floating point didn't actually become common as a small historical aside. They started using it in the 1960s. It had actually been proposed in the 50s, and John von Neumann rejected it because he didn't like the inability to reason precisely about what was going on with it. So I feel a little bit vindicated when I learned that fact. All right, let's see. Now, that's a little bit more urban. Okay, that's fine. Now, what we're at today is a situation where we have a standard, IEEE 754. This is a hardware-software specification, which means that it tells you what the behavior should be on hardware if you adhere to this standard, to this specification, and it tells you what your software should expect. But there are several things wrong with it even as a standard. Now, I understand historically it came out of a number of compromises. There are certainly reasons that the people who have produced systems that are not compliant with 754 in all aspects have thought were justified reasons at the time. It's fine. But we have to live in the world where this is the case. So one of the issues that's kind of interesting, and these are starting to get away from the 1.1 minus 0.3 minus 0.8, like completely deterministic thing. Now we're wandering, through the dark woods. Like we are wandering into a world where these are non-deterministic errors because they are not predictable in the behavior of the system here. So the first of these are discretionary or optional or advisory aspects. It turns out that there are a lot of things that 754 as a standard suggests, sometimes strongly, sometimes gently, that you might think about implementing on your system. And it also turns out that these things materially impact the behavior of the kinds of things that are on your system. One example of this is exception handling. So what happens when you overflow a number on a system? So naively, if you're running on commodity hardware today, and you add together 1 times 10 to the 308th and 1 times 10 to the 308th, what do you expect to get back? No, it actually doesn't overflow to NaN, because NaN's reserved for like 0 divided by 0. You might get a NaN, but but actually we're sort of getting into murky water here. So positive infinity is naively what you'd expect. There are chips that do not overflow. They remain at the maximum saturated value. So you add that value together. You don't get 2 times 10 to the 308th. You don't get positive infinity. You don't get NaN. You get the same number back. There are 2 kinds of NaNs that can happen if you run into a situation where you have gotten a NaN. There's a quiet NaN and a signaling NaN. Signaling NaN, in theory, was introduced in 2008. The idea was that it would give you information about what failed and why in a way that allowed you to use it or reason about it in some way. And then in practice, no one ever actually did anything with this information, so they took it out in I think the last standard was 2019, I think was the latest 754. So they removed it again because it wasn't getting used. You have subnormals, which are a way of representing values very close to 0. It's sort of avoiding an underflow. Like, why don't you want to hit an underflow? Because you don't want to accidentally get a division by 0. So a subnormal is this, they define this way of using a 754 float in a way that you don't actually underflow as you get closer to 0. You just get smaller and smaller values for some range. There is what's called extended precision arithmetic. We're going to look at some examples in C of this in a moment. We get some very interesting behavior from that. And that's an optional characteristic where you do a computation between 2 values, but the intermediate value is allowed to assume more bits. And then you do the computation with those extended bits, and then you truncate it in some way when the value comes back into your assignment. And that has some interesting ramifications. The next one of these I want to look at is gaps or omissions. And this actually refers to places where 754 does not specify correct behavior. It doesn't specify behavior. It says you can do this, but I'm not going to tell you what the right answer is. So this is mixed precision operations, for instance. If I have a double, then I want to know what's going on here. This is a function of rounding modes. It's a function of precision loss. It's a function of extended precision if it's present. It's a function of presence or absence of dedicated hardware in certain cases. None of these can be known to you as the programmer just writing this for an arbitrary platform. You don't know what's going to be there. There are, believe it or not, as horrible as this may sound to you, a spec is only worth the paper it's printed on. Sometimes this has been my mistake. There was a floating point division bug on Pentium chips in the 1990s. That might be me bumping this. Okay. That they were actually using this clever lookup table to help them do floating point calculations more quickly, but then the lookup table was wrong for certain combinations. So, FDiv was broken for a few years around 1994. And then another one is, for instance, I mentioned there was a chip that didn't overflow. This is a Motorola phone chip. It's not in production anymore, but there was a Motorola phone chip that didn't support NANDs or infinities for some reason, which is sort of odd because they're still using the 32 bits or the 64 bits or whatever, but they're just saying they're not going to use certain parts of the spec. So, failure to actually follow the spec. However, one of the ones that is most frustrating to reason about is compiler optimizations. And what this means is that in most platforms, most of the time, the compiler reserves the right to change the sequence of your calculations, which, as we just saw, can materially change your result. There are things you can do to mitigate this, like volatile, but it turns out that the C volatile keyword is the manufacturer's recommendation of what you should do with that register. It just tells you that it's liable to change and you should check again. It doesn't tell you that you're actually going to get the certain behavior that you want. So there's all sorts of crazy things there. We're going to look at fused multiply add in a moment, which is really just wild. And the thing is, this is opaque too, because this depends on your hardware and your compiler stack and the various flags that you've passed to this. It's really, really amazing, like, what's going on here. Then there's rounding mode. Okay, so we didn't really look at rounding mode, but when you do mathematics with binary, you have to make a decision about when you have the result and you know that there are additional bits in this result that you're truncating, you have to decide how you're going to truncate that value. And you have several options. One of them is you can always truncate down, or round down, I should say round. You can always round down. You can always round towards 0. You can always round up. You can always round away from 0. And there's one more, but it escapes me right now. And what turns out is you can set this rounding mode because you're trying to get a target behavior. The rounding mode on the CPU can be changed by other threads on your system in the middle of a computation. This is a documented situation that occurs in certain cases. So it turns out, for all of this, we can't get determinism out of 754. All right, I'm going to look at a couple more examples here, and then we're going to switch. I mean, this is really interesting. We're going to talk about how to get out of this situation, because we'll be in the second half. Okay, so here we have a C program. And this C program has a couple variables, A and B, defines a function. X is the sum of A and B. If X is not equal to A plus B, print F. What will this program do? It is unspecified. This is unspecified behavior in C. And the reason is because you don't know, when you do this calculation A plus B, this summation can occur with extended precision bits. But when the assignment takes place, it is coerced back into a 64-bit double. When it is compared here, this may still be carrying the extra precision bits in the registers, which means you actually don't know what the answer to that comparison is. Which is why part of the moral of the story is never do equality comparison with floating point, but that's a whole other story. All right, so the problem I've been dealing with for a few months now is, okay, great. Like, this is the world we live in. I can't do anything about 754. I can't do anything about hardware. So what's the way out? Like, how are we actually going to solve this problem in some way? Because there are parts, I mean, even if, I'm working on a numerics library in Urbit, but even if it weren't that, we have a WebAssembly platform, and that's going to use floating point. And so it's going to run into the same sort of issue where you want to run things deterministically, but you're running on floating point. So, we're going to run up against this as a deterministic platform sooner or later. So, as I see it, there are sort of 5 avenues of investigation. We can look at hardware, we can look at software, we can look at treating as what I'm calling it an opaque calculation, which means sort of treating it like a network call, where I'm sending data out, I'm getting data back, but I'm sort of agnostic about how that data are obtained on the other side. I can cache the results, which is kind of an interesting approach that was used by Sun's Spark architecture in the 90s. Or we can do something else entirely. Let's not do 754. Let's do something else. All of these have compelling reasons to pursue them. But first we have to sort of decide what these mean. So if we're talking about hardware supported, what I mean by that here is if we want to have hardware supported 754, given the kinds of things I've talked about to you a moment ago, what does it mean to actually control the stack? Okay, so there's like the first thing I came up with is like, well, what if we could just actually set the right flags on the compiler when we do the build? Well, okay, so this requires you to sort of have a lot of information about, is the behavior compliant? Do the optimization flags that you're using actually produce the results that you use? And keep in mind that any deviation from determinism in the sense that we're talking about breaks the guarantee of referential transparency that we want to keep, right? It sort of feels minor, but it's breaking a guarantee that you want in the system as an invariant guarantee of the system. So you don't know exactly what you mean by control the stack. Worse, fused multiply add is a one-step operation. Typically, it's implemented as an assembly operation. And so if you're doing a calculation like this, A times B plus C, fused multiply add is a 3-input operation that will do the calculation all at once for you. And in this case, for this calculation, it turns out that if you use -03 and you get FMA, you do the compiler optimization here, you get 6.3658, which is correct. And if you do -00 and you suppress the FMA optimization, because of the way the bit horizon, numerical horizons strip out information, you get the wrong answer. So this is a case where FMA gives you the right answer and the slow way gives you the wrong answer, just because of correctness here. Now, there's another example here where if you're doing A times B plus C times D, and for some value of C, some value of D, there are a lot of values in C and D for which this is not, this will work just fine. But there are values where this can have problems. And then A is C and B is negative D. So essentially what you're doing is you're wiping this out. If you FMA A times B, C times D, you get the wrong answer. And if you do it in 2 steps, you get the right answer, because it actually lets the two cancel each other out at the same thing. So here we have a case where if we optimize the first time, we get the right answer, and if we optimize the second time, we get the wrong answer. So I'm not convinced that saying control the stack is actually a meaningful solution, just given the vagaries of the system on the ground. Another one is to simulate platforms, and we talked about, well, what if we knew what the chip behavior was, and we just logged that when we did, when we evaluated the runtime, we recorded this in the log somehow, so that we knew what platform had carried out this calculation. Well, the big problem with that is, do you suppose that this is actually documented in any sort of way that would let you recover this information? And it becomes combinatorically explosive once you start counting in compiler options and compilers and chipsets and everything else that can go on, right? So it's a non-starter. There's just no way to do it. Now, another interesting one is to support only a single hardware for the lifetime of the instance. This is actually viable for certain kinds of operations. right? You can think of this as kind of like a cloud operation or a bot operation. You're going to spin something up, you're going to let it run for a finite lifetime, and then you're going to terminate it. And it is deterministic within that scope. So, we'll revisit this one. Another one that we talked about was the possibility of docking floating point results, sort of like trimming off the trailing bits in a way that would let you treat the result, like ignore rounding modes and those sorts of things. We've kicked it around, but I'm not convinced that we're actually going to be able to come up with a mathematical formulation of it that's rigorous enough to satisfy here. So I'm not real keen on that one. And then number 5 is check consistency, which is to run the calculation on the platform in Hoon and Nock, and run it on your hardware, and then see if they're the same. Well, the problem with that is you've done the calculation twice, and you did it the slow way, so you gain literally nothing by doing that. You gain the assurance that the hardware did what you thought the hardware was going to do, but you don't gain anything else by it. All right, so the next road to go down, software defined. Now, the nice thing about software definition, and there are packages for this like SoftFloat. This gives you formally correct behavior to whatever standard the underlying library purports to satisfy. Urbit uses SoftFloat for conventional floating point calculations today. The downside is it's software, not hardware, so it's just not as fast. But it is a reasonable solution as far as if you need deterministic results, this seems to work well for you to just do it in software. However, the caveat on that is if you're going to calculate transcendental functions, sine, cosine, exponent, exact answers for these, and we're going to have to draw a distinction between exactness and reproducibility now. Exact answers are not known in many cases, which means that if you're specifying a solution in Nock that you need your hardware to reproduce exactly, you have to make sure that you're following the same algorithmic path on both, because you can't have differences in the final result, which means you have to calculate them in the same order, in the same way. Let's see. Oh. Sorry, wrong window here. All right, let's see. That's okay. Then opaque calculation. Okay. All right, opaque calculation. This is the idea that when I need to do a numerical calculation, I don't treat it as here is the equivalent Hoon or Nock specification on my system, and I'm going to run faster C or C++ or Rust code that's equivalent to it. I'm saying I have this magic phrase, and I'm going to shout it out into the void, and whatever the gods hand back to me is correct. And this is kind of how a network works, right? Like from Urbit's perspective as a system, there's a sense in which Arvo, the operating system, doesn't know about the outside world. Like it issues hints to the runtime that result in Unix side effects, and it receives injections from the Unix host system. But and this is what generates an event, but it doesn't sort of know, in a sense, about what's going on outside of itself. It's sort of agnostic in that way. There's a world out there that it receives things from, but it doesn't necessarily have to reason about every single one of them, as for instance with networking, right? Someone can send me a message. I didn't hope for that message, right? Someone pings me. I didn't know they were going to ping me. This is a little bit fuzzy of a model. We could do it this way, and I think there's actually going to be some good cases to do it this way. It's sort of aesthetically less satisfactory than doing something that is deterministically correct compared to the Nock you are also comparing it to. A very interesting possibility is the idea of caching the results by call site or some other mechanism. And what this means is that when you've calculated any particular floating point operation, you store it in a table. And if you need to do that calculation again, first you look and see if you have that calculation in the table. Now, it's probably true that a lot of calculations are repeated over and over. So, maybe this is a possibility. There's going to be some overhead on your lookup table time. Like I said, the Sun Spark architecture actually did something similar, but they did it for errors. Whenever they ran into floating point errors, they would log the errors in a lookup table by call site, and then you could go back to the table and figure out where this had come from and why. But in general, it seems like if you're doing anything really interesting, you're going to end up with, huge combinatoric explosion of results that you don't really want to store everything of. And then the final value, and I better keep an eye on my clock here. Where have I stuck it? Let's see. Okay, I've got a few minutes. The final option is to do something that's a roll your own. So you don't have to do IEEE 754. There are people doing bfloat. There are people doing other kinds of tensor systems today that are not 754. Some of these people, like Google, are big enough that they're actually getting dedicated hardware to run bfloat and other kinds of operations that they're doing. So if you have the clout to start producing your own hardware for your own implementation, now you're talking about a system you actually can guarantee in hardware is deterministic, is fast, has all these other nice properties that you'd like to have. Another thing that I've been very intrigued with, and I want to explore more, is the idea of actually jettisoning floating point again and going back to doing fixed point calculations for a lot of things, where we can just do, basically, the nice thing about fixed point, where your point, you're basically like picking a scale, think of it that way. It means that all of your operations are now effectively integer operations, and they're taking place at integer speed. And all of the ramifications and elaboration of what that means takes place in your software. But when you actually ask the CPU to do a calculation for you, it's doing it as an integer calculation, which are much faster, much more nicely behaved, completely portable. You might have to worry about some things like big ints or overflows and these kinds of things. But in general, I think that's another attractive thing that I'd like to approach. And so right now, if I look at the candidates that I consider most likely solutions here, the pros of going to hardware floating point on a single machine for its entire lifetime is it's good for a finite lifetime when you know you're going to be running that system there. The con is that things may not actually work out that way. You may not actually want to be running the same machine. We don't know what the future architectures are going to look like. And we'd like to have full event log replay on any future system. So probably not ideal for most applications that people are doing. But again, like bots or something, it's absolutely fine. All right, we're going to go with software. Then we can get 754 compatibility. This is actually one of the roads I've gone down more recently, is re-implementing the BLAS library completely in software, so we get this quality for it for the vector library that we've written. The cons is you don't get the hardware acceleration, so you're taking a hit there. And the exactness comes back because, so what I mean by exactness is that there is, when you calculate the cosine of 0.547, there's an exact answer to that. And when you type cosine 0.547 into a floating point system, the number you're getting back isn't the exact answer. But the exact answer can be known and it can be calculated. And for instance, I think for all values of sine of C single precision floats, I think the entire range of 4.2 billion values has been calculated. Like we know that, we have solved that problem. It requires calculating every answer with hundreds of bits of accuracy to have it, which means we don't have it for double, for instance. But anyway, that's where you run into the exactness versus precision there. Opaque callback, looks like a network call. The big con is that it's just a more complex design pattern. It's just harder to write this kind of code in a way, and then you have event log issues, and it breaks synchronicity and stuff. But I think that doing this two-level approach, easy software floating point, fast hardware floating point, could be an interesting way to go. Liam, were you going to? But you have to be fast to do that lookup over the field of possible values.
Yeah,
right? Like, I mean, in principle, yes, looking it up in the book would be wonderful. In practice, there's going to be latency around either option, and so you'd have to weigh those. Cached results by call site. You know, it renders the floating point FP computations referentially transparent. It's nice on that, but you know, again, the event logging could become too big. And then the other option is to go through IEEE 754 in hardware, or utilizing something. What this is building a library that uses parts of 754 that are known good, and then you have to enforce the programmer discipline of you are only using the parts that are known good. You have to use this library, and that way you do get the benefits. I still think there's some questions around compiler optimization in particular to be worried about, but yeah, unknown degree of vetting required. There's a lot hanging on those words. All right, let's see. Yeah, and then posits are actually the other thing. Unums are I'm pretty interested in, which are another formulation of floating point that's not IEEE 754, but it seeks to solve some of those problems. One of the nice things is it does it in 32 bits. It solves a lot of the issues with 754 determinism and non-determinism, but it does it in 32 bits instead of needing 64 bits. So that's probably where we'll end up in the near future as we continue to investigate this approach. Thank you. Questions, or am I about to get yanked with the hook off stage?
I guess one of the parts is on the hardware side, you could probably just create your own FPGA implementation of your own software version to get the benefits of the software with the benefits of the hardware without spending like millions or billions of dollars to manufacture your own hardware. So that's kind of the other.
Right, so you could do FPGA stuff. We actually have an interesting case where Native Planet is building a NOC chip, an FPGA that implements NOC as its RISC language. He hasn't done anything. Native Planet is a company in the Urbit ecosystem. He hasn't done anything with floating point insofar as that goes. Like, it's just calculating pure NOC expressions instead of doing anything fancier than that. But yes, like the FPGA or even like ASICs or something, like there's some interesting roads you could go down where if you can guarantee that behavior, you have some options open to you. But those are all, I mean, FPGAs are okay, but anything more than that, you're starting to get into heavy capital outlays to make it possible. So. They're probably of commensurable difficulty to implement in software. You know, if I were, like, there is a soft float library that implements 754 in software. There's a soft posit library that implements John Gustafson's Unum's posit system as well. I don't know if it's complete or not, but I know that it exists and is being worked on as an active project. If you were going to go down other roads like bfloat or something, presumably at this point you'd just be running on the hardware that's designed for that. I don't know of a software implementation of it, but I don't think it would be any worse than doing what's already done with these. Basically, the thing is you're doing a lot of, you know, you do like bit masking, and then you have to decide, okay, based on my exponent rules, how am I going to combine these two significance and everything. Well, we don't know until they get there if the hardware manufacturers are going to actually comply to the new spec or not. Oh, bfloat? I could. I mean, like that's the sort of thing one could do as an investigation. I don't know enough about bfloat myself to know about going down that road, but I do know that it gets used in machine learning, so it's of interest. Is that a question or stretch? It was a pretty gratuitous stretch. Yes?
I was going to say it is a lot of work doing software floats. We have hardware compatible 128-bit decimal floats in our system.
Yeah. I'm not surprised it's a code grind to get those things built.
Well, part of what I was thinking is sometimes just, I have found it very useful occasionally to just ignore the 64-bit limit and sometimes say, well, it's actually easier to just bump the bits on it and accept it inexactness in the lower bits because you just have enough bits to do it. I've used that on some benchmarks, for instance, like the NAS parallel benchmarks have a random number calculator, and they have you doing 64-bit flow tricks to get around the precision limit. And all I had to do was I would just bump the algorithm into 128 inside the algorithm, and I could just directly use the math formula, and the rounding errors were not an issue.
Mhm.
Maybe throwing a few more bits at it makes certain things go away. Maybe theoretically unsatisfying.
I mean, there's a reason they do extended precision intermediate results. Yeah. All right, thank you.